Hi, I am Brian, and I'll introduce ExactNerve, a precise volumetric parameterization for neural gradient fields. We explore the integrated positional encoding of MIPNerve, which summarizes the positional encoding in a volumetric region defined by the conical frustum. While this IPE is defined as the integral of the positional encoding function divided by the volume of the region, it doesn't have an analytical solution. For this reason, MIPNerve approximates it with the expected value of a multivariate Gaussian that fits that region. Instead, we decide to switch from cones to pyramids, and by using the divergence theorem, we get the analytic expression of the IPE in terms of the vertices and normals of the pyramidal frustums. Our formulation is competitive with MIPNerve when testing it on the Blender dataset. Additionally, it is still competitive when compared with MIPNerve 360 without any additional change in our formulation. Despite a slight decrease in performance, we observe that our formulations allow for better distance depth estimations. Our work is motivated by the gains in accuracy of MIPNerve when compared with the original implementation of NERV. NERV performs a color and density estimation of points sampled along an array that passes through the center of a pixel. These points are transformed using a positional encoding function, which is a composition of sines and cosines to induce higher frequencies. However, this strategy may cause ambiguities that ultimately lead to blurring and aliasing. In order to reduce this, MIPNerve performs a volumetric positional encoding by considering a cone that passes through a pixel, sampling cone frustums instead of just points. MIPNerve defines an integrated positional encoding that is the integral of the positional encoding function divided over the volume of that frustum area. This formula has no closed form solution, so it is estimated using a fitted 3D Gaussian and this expected value of this region. With this implementation, MIPNerve prevents aliasing and reduces blurring. However, the Gaussian approximation degrades for large regions, which are located far away from the camera. This is usually not a problem for bounded scenes, such as the Blender dataset, but it can be for larger scenes, such as the 360 degrees photographic scenes that are in MIPNerve 360 and that they have a background. For this reason, we introduce ExactNerve, which replaces a cone frustum by a pyramid that passes through the corners of the pixel. Our research question is then if this change in parameterization would enable analytical and exact solution and how this implementation compares with MIPNerve. In order to calculate an exact integrated positional encoding, we transform the volumetric integrals into surface integrals by using the divergence theorem. Now we focus on finding different functions f that are suitable for our problem. For instance, the denominator, which is in fact the volume of the pyramidal frustum, can be obtained by choosing this function. Then, using the divergence theorem, we obtain the following surface integral. By analyzing the shape of the pyramid frustrums, we can divide the faces into triangles without losing generality. Then, by using the coordinates and normal vectors of these triangles, we obtain the following expression of the volume. This expression is in fact a well-known expression for the volume of a parallelepiped in geometry. We can use the same strategy with the following function for the numerator. This is valid for the x-coordinate and the sine function of the position encoding in NERV, but a similar analysis can be done for other coordinates and for the cosine function. This final formula of the numerator for the k-coordinate and the L frequency is given by this expression, where capital X tau is a matrix containing the coordinates of the vertices of the triangle. It is worth noting that this formula is valid for any parallelepiped shape and not only the pyramidal frustums. This fact is exploited by implementing ExactNerve in the MIPNerve 360 context that performs a contraction of the space. So this contraction will ultimately lead to a deformed pyramid frustrum that can be still calculated using the same formula of our exact integrated positional encoding. By comparing ExactNerve with MIPNerve in the Blender dataset, it can be observed that the reconstructions are quite similar, with a slight decrease in the performance for the PSNR and the SSE metrics, and a slight improvement over the perceptual metrics that are LPIPs and DISTs, with an exact same value for the average value here. You can observe in these results that the quality of the images are quite similar for both cases. As noted earlier, our method can be applied to MIPNerve 360 for unbounded 360 scenes. Although our method has a slight decrease in performance, it is still competitive. It also shows some interesting qualitative results. For instance, our method is prone to error for tiny vessels that are close to the camera, as in the bicycle cable here. However, it exhibits a significant improvement on distant objects, such as in the cleaner reconstruction of the grille and the car in the bicycle scene, as you can see here and here. This is our method that is a bit cleaner. Or the background reconstruction of the garden scene, where several objects are kind of occluded in the MIP-NERV 360 here, but here are completely reconstructed. There are some gains in the background regions of the depth estimations. The previous car and the grille reconstructions of the bicycle scene are cleaner for ExactNERV in the depth maps. In the bonsai scene, some improvements are noted in the Y supporting pole, the back of the chair, and the window area here. Similarly, there are several objects in the background of the garden scene that are reconstructed better with our approach. Our method is prone to numerical underflow, given some small numbers in the numerator of the exact integrated position encoding. The following image shows an example of the regions showing in this numerical underflow behavior, which happen to be where two coordinates are too close. The curvature of these regions is a footprint of the contraction function in MIP-NERV 360. These artifacts can be mitigated using L'Hopital's rule, and for more information about the formulation, please read our paper. In conclusion, ExactNERV is an alternative parameterization for the volumetric position encoding of MIP-NERV that use pyramids instead of cones. Our approach has a similar performance compared to MIP-NERV, and it can be implemented right off the shelf in MIP-NERV 360. ExactNERV shows a better reconstruction of background objects. This indicates that probably a hybrid implementation of MIP-NERV in the nearby instances and ExactNERV in far objects might be ideal. The key idea of ExactNERV can be exploited in different applications. It also enables future exploitation of new position encoding functions in the NERV context. Thanks for listening, and don't forget to visit our poster or project site. Thank you.